All right, so I'm going to take 1 minute before I even get started on these questions and just give you a rough idea of how this video should be used. Number one, uh, pause it, rewind it, get better as you go along. If you don't understand the questions after going through this video and checking your work, uh, then absolutely ask me as many questions as you want. Number two, I am going to look at the questions beforehand. I'm still going to do the same way I do other questions, saying, hey, I'm looking at the diagram if they have a diagram, or I'm looking at the answer choices. I'm still going to do that, but I am going to try to keep it a little bit tighter of a video and a little bit faster to save you some time. So I am going to read through the question, figure out my answer, um, and have all diagrams and things underlined that I need to have underlined to, again, save you as much time as possible. If you prefer the other format where I do it raw and work through the questions with the video so you can see my entire thought process, please, please, please let me know and I will go back to those. But I figured I would try something different and see how you like this. All right, without further ado, let's jump to number 47. 47 is a rocket accelerating away from Earth. I'm assuming at this point, and with all questions, you have read through the question, you've tried the question on your own first. That should be a goal. We have our answer choices, which are discussing the energy. The first one is the rocket's energy. The second one is the system gravitational energy of the Earth rocket system, or the potential energy of the Earth rocket system. And the third one is the mechanical energy, which again is fancy for total energy. And for each one, I'm looking at the answer choices. They're all increasing, decreasing, constant. Those are our choices. So while I'm reading the question, I'm paying attention. Is it increasing, is it decreasing, or is it remaining constant? Well, the rocket's kinetic energy. The rocket's going up, but you had to pick up on this detail in the beginning. It's accelerating away from Earth, meaning it's getting faster away from Earth. So if you missed that detail, you wouldn't have realized that it has to be increasing for the first column. So it should be getting faster because kinetic energy is just 1/2 mv squared. So if v is getting bigger, k is getting bigger. Now I'm looking at the second column, the system's gravitational potential energy, or MGH, right? And they're saying of the Earth rocket system. So because they're including Earth or the rocket, that means potential energy counts, right? If you see the word Earth, like they have in both part 2 and part 3, the potential energy is increasing. The potential energy must be considered, which already brings me to my next point. M is constant, G is constant, but if it gets higher, potential energy is increasing, which rules out option choice C. Now we have the mechanical energy, but because mechanical energy is the sum of all other energies, kinetic and potential, if kinetic's increasing and potential's increasing, then mechanical energy must also be increasing. So the answer for that one is A. Wrong button. All right, so for number 48, there's a couple of things that I picked out from the question. Number one, it's released from rest, and it's released from the horizontal, which means it starts at position A, and swings down to position B. And from the answer choices, I gathered that they wanted to something about the angle. I don't know what that is just from looking at the question, but then I realized they want us to know, well, if we assume that gravitational potential energy is 0 at the bottom, they want us to know when it's half potential, half kinetic. And you would think, oh, when it's at half the height, it should be an angle of 45 degrees, right? It's halfway down. But based on how circles work, that's not how it works, because it goes down a lot in the beginning and it goes down less towards the bottom, right? Because it's going flat at the bottom, so it's not really changing its height so much at the bottom. And it changes its height a lot more. So from that, you could have kind of made the assumption, oh, at half the height, it's got to be closer to the top. And if that's a sufficient enough answer for you, you can go ahead and say, yeah, it's less than 45 degrees below the horizontal. However, if you want to see a mathematical explanation for what the angle, and actually see a calculation of what the angle actually is, I'll work through that for you. So I know that we're trying to find this red angle theta right here, and we know the length of it because at the bottom, the full length is height h. So the radius is the height that of mgh, right? So if the radius is h, and at half height it's h over 2, well, now we know the opposite side is h over 2, because if this side is h over 2, this side's also h over 2, and now we have this wonderful red triangle right here. And you can use sine theta equals opposite over hypotenuse to calculate what the height would actually be. So sine theta equals opposite, h over 2 divided by hypotenuse, h. And the h's will cancel, and then you're going to get sine theta equals 1/2. And when you take the inverse sine of both sides, you're going to find that the angle is actually 30 degrees. 30 degrees. That's a 30-degree angle in there, which is less than 45. So you could have thought about this conceptually and gotten there quickly, or if you wanted to double check, or you couldn't figure it out conceptually, or you were unsure of the drawing, you could have mathed it out. So there's two different approaches to that problem. All right, so 49, my first thing, always I look at the answer choices. They're really wordy, and I immediately skip out of them because I can't see any patterns. I'm not seeing similar things in each one. I have no idea, so I'm going back to the question. Again, don't waste a ton of time looking at the answer choices. Just use them to give you a gauge of what you're paying attention to. And this question's so short, my brain's immediately saying, just read the freaking question. So a ball is tossed straight up and returns later to the point from which it was launched. So ball goes up, ball goes down. There is air resistance, and there is gravity. And then I'm just going to go answer choice by answer choice. The speed that the ball returns to the point of launch is less than the speed it was launched at. Well, it starts with kinetic, which turns into potential, which turns back into kinetic. And we can ignore gravity in terms of energy, because if we're including Earth as the system, 100 joules of kinetic without any other forces, well, because of the force of gravity, turns into gravitational potential energy, and then turns back into 100 joules of, kinetic energy. So if there's no other outside forces, it should remain 100 joules the entire duration. However, the speed of the ball returns, and regardless of whether there's 100 joules, it's still kinetic at the bottom, potential at the top, and kinetic at the bottom, right? We'll call this A, B, and C as we go. So as we go from A to B, there is air resistance, so we're going to have less joules of energy. So I'm going to just say, okay, we've lost 10 joules from air resistance. I don't know how many there are, but I know we've lost energy as we've gone up. As we come down, air resistance again, as the ball is going down, it's bumped into air molecules which are pushing it up. So on the way up, air resistance is working against it, stealing energy. On the way down, air resistance is up, still working against it. So we're going to have even less joules of energy there. So we're going to have 80 joules of energy, and if all of our kinetic at the end at point C is less than our kinetic at point A, then the speed has to return at less of a speed than when it was launched, which is different from kinematics, which always assumed air resistance is negligible. So in that unit, you usually assumed air resistance was negligible, and it would return with 100 joules or the same speed. But in this, because there is air resistance, it's losing energy the entire way, which turns into movement of the air molecules that it's bumping into. That being said, I'm still going to go through the wrong answer choices and prove why they're wrong, because I'm sure a lot of people would like to see that. The time for the ball to fall is the same for it to go up. That's a tough one. And for that, I actually went back to kinematics. V equals V naught plus AT, which I rearranged to V minus V naught. So I brought this to the left side. I subtracted it from both sides. Or the change in velocity equals acceleration. Actually, we're trying to find, the change in velocity uh, divided by the acceleration equals time. And for that, I forget how I got that. What did I say? Oh, in that case, when it's going up, you have the gravity and air resistance both pulling down. So there's a bigger net force down, which means there's a bigger acceleration. I actually don't think you can use this because the change in velocity up is not going to be the same as the change. Oh, it is the same because the air resistance force. No, the air resistance force is bigger the faster you are, and if it's falling slower, then it's not the same. So I actually can't be wrong. But if it goes up the same distance, but it's falling slower on the way down, then it's going to take more time on the way down. That's why it's true. That's actually, I guess, the third kinematic equation. No, it can't be. It would have to be the second. So same distance, but it's slower on the back half, which we proved in part A, which means more time to fall the second half, because it is the same distance up, same distance down. Those are the same, but the velocities are different. C, the force of air resistance is downward in both situations. We already said air is down on the way up because it's pushing through the air, and air resistance is up on the way up, so that rules out C. D, the work done by air resistance during the flight is zero. No, work takes energy away. The one situation where you might have gotten that off was you could have said, oh, it's removing joules on the way down and adding joules on the way up. No, it's working, it's stealing joules this way and it's stealing joules this way. So it's negative, it's taking energy away in both situations, or it's subtracting joules. So it's negative plus another negative. And negative plus negative equals negative, which is not zero. So D is out. E, the network done by gravity on the ball during the flight is greater than zero. Work done by gravity. Well, in that case, I'm going to go with the work equation, force times distance. Well, the force is mgd, same mass ball, same gravity, and same distance up as it is on the way down. And gravity removes joules of energy on the way up, and it adds joules of kinetic energy on the way down. So in that case, you would have to assume that Earth is not a part of the system, it's an outside force because it is doing work. If something's doing work, it's not a part of the system. So I hope that helps for that one. All right, so number 50 is a doozy. I don't expect anyone to have gotten this, but it's a good learning tool. So if you've read the problem, we have 4 intervals, interval 1, 2, 3, and 4, for a block on an incline, and I've drawn them over here. This is phase 1, phase 2, phase 3, phase 4. And in this diagram, we have, for each of these intervals, the amount of energy dissipated due to friction. So during phase 1, there was no energy dissipated due to friction, which they said in the question. During phase 1, the block slides without friction. And then in the other 3 phases, there are varying amounts of friction. So we need to figure out, okay, how much friction is there? And the easy thought would be, well, work is the change in kinetic energy, so whichever one it gets rid of the most kinetic energy would be the most work done by friction. But you have to consider that there's 2 forces contributing to the work in this situation. We have the FGX component down the slope, and we have friction backwards. In phase 1, we only have friction. So now that we have that kind of general understanding, we need to figure out, okay, if we're trying to calculate work equals FD, we need to figure out which one has the biggest F times D product. Well, we already know that the force during phase 1 is going to be equal to, or proportional to, this slope, because slope, rise over run, is change in velocity over time, or acceleration, which is proportional to the force, or in that case, because it's only gravity, FGX. So in this case, there's an unbalanced force causes an increase in velocity or a positive acceleration. During phases 2 and 4, the forces have to be balanced because it's a constant speed. So phases 2 and 4, the forces are balanced. During phase 1, FGX is bigger because there is no FGY. And during phase 3, hopefully you realize because it's slowing down, that means the leftward force has to be greater than the rightward force, or rather friction has to be greater than FGX. So in this case, I'm going to use this slope to be kind of my baseline. Here the forces are balanced. So during phase 2, the friction, and I'm going to switch colors so you can see what I'm doing as I'm going, but friction is equal to the weight, or FGX, and that's also true in phase 4. Friction is equal to FGX. In phase 3, friction has to be greater than FGX. Hopefully you guys understand everything I've said up to this point. Constant velocity, balanced forces. Slowing down, backwards force is greater. Speeding up, forward force is greater. That's all it boils down to for the first thought process. So from there, I made the immediate logical leap, hey, if that's true, and work is equal to FD, then whatever has the bigger force should yield more work, right? Which would seem like it's the case. But when I said, okay, well, in phase 3, that's where the work done by friction has to be the greatest. So I guess they just didn't put an F, but the frictional work of 3 has to be greater than 2, which is equal to 4. And I'm so glad this wasn't an answer choice, because that's not a possible choice we have, which means I'm missing some detail. And that detail is they're not traveling equal distances during each phase. In phase 2, it's traveling a greater distance than it is during phase 4. And from here, you can really likely logically make the leap that 2 has to be less than 4, I think. Oh, yeah, it's going to cover less distance during phase 4, which means during phase 4, it's going to do more work? Give me 1 second to think. No, during phase 2, it's going faster, so during phase 2, it's doing more work, more distance. So phase 3 wins by a landslide because that's such a huge frictional force. So 3 is greater than 2 is greater than 4. And conceptually, that's it. If you wanted to go in depth, you could have literally calculated the D as area under the curve, right? Because area under the curve would be velocity times time, and the change in velocity times time is equal to the displacement. So you could have done that to further prove this more accurately, but really what we did here is sufficient to accurately conclude that C is the correct answer. And I want to point out that was a hard problem, so don't feel discouraged if you missed it, but you should also learn from it and pick up maybe 1 or 2 skills from it. All right, so for 51, I immediately see we have a velocity time graph. I'm thinking slope and area under the curve. Slope is acceleration. Area under the curve is velocity times time, which is displacement. So slope, area under the curve. And then I'm immediately jumping to the answer choices. They are numbers, so we're going to have to do a calculation. And it's in joules, which means we're going to figure out something about energy or work. Those are all my initial thoughts looking at this problem before I start reading. And when you read through this question, you see there's a half kilogram block being pulled with a constant rope T. And in this graph, there is no friction. So during phases 1 and 3, there's no friction. And during phase 2, there is friction. And I also know that it's speeding up with an equal slope, equal acceleration, which makes sense because if it's a constant force during phases, or the same force during phases 1 and 3, it should be the same acceleration during phases 1 and 3. In phase 2, they've added friction, which has to be greater than the tension force because it's slowing down. So if it's slowing down the force backwards, friction has to be greater than tension. But then you read the next part and you find out that the entire amount of information you read up here largely is extra information that you don't need. So we have another block initially at rest, so same starting position, and no frictional force during phase 2, which means if there's no frictional force, the graph is going to continue, and I'll change colors so that shows up differently, which means during phase 2, it's going to be continuing in a straight line along that same acceleration slope that we had during phase 1. So the object's going to continue here all the way up the entire time. So instead of going back and slowing down, constant tension force with no other forces means constant acceleration. And they want to find the object's change in kinetic energy during this segment. How do we figure out change in kinetic energy? Well, my first thought when I see that is work, which is equal to force times distance. And I suppose we could use phase 2 to figure out how much friction, but I don't think so. I don't think you could solve for it. I could be wrong. If you find a way, let me know. But that proved to be a dead end. But we can go more simple. The change in kinetic energy is equal to your final kinetic energy minus your initial kinetic energy, or 1/2 mv final squared minus 1/2 mvi squared. And they specifically said during phase 2. So that would be from here to here. So we need to figure out the change in kinetic energy during that phase. They give us the mass, so that's given. We can plug that in for both of them. The initial velocity during phase 2 is 4, so we could plug that in. Oh, I dropped my V. We can plug that in. And the final velocity is not on this graph, but if it goes up 4 every time it goes over 2, it's going to go up another 4 as it goes over another 2. So it goes up 4 meters per second in the first 2 seconds. It's going to go up another 4 meters per second in the next 2 seconds. So the final velocity should be 4 plus another 4, or 8. So you plug in your mass of 1/2, you plug in your final velocity of 8, and you plug in your initial velocity of 4, and you should get 12 if you do your math correctly. All right, so 52 is completely a conceptual, do you get this situation? So figure 1 is just an uncompressed spring. Figure 2 is the height that it's at, the equilibrium position. Figure 3 is where they push that block down and then they let go of it. And they ask, where is the kinetic energy at a max? Well, once the block reaches the equilibrium position, the spring will stop pushing it. Or at least the spring will not expand as quickly as the block. So at that point, the block is released. And once you pass the equilibrium position, because the block is going up faster than the spring is, the block will slow. The only force acting at that point is Fg, which means it's immediately going to slow down, which makes sense. When you leave a trampoline, your spring energy stops giving you kinetic energy, and now you have a max kinetic energy the second you release. You're fastest when you're first thrown up in the air. So for that one, it should be C. This figure 1, red herring. All right, so there's a lot to unpack with 53, but basically we have a cylinder and a sphere. Cylinder and a sphere at the top of this 1 meter high ramp, which is at the top of this. It gets to the bottom, rolls across a smooth thing, and the cylinder lands here, and then they replace it with basically a lighter sphere. That's what they were talking about with rotational inertia. Less rotational inertia. Inertia is how hard something is to move, so rotational inertia is how easy it is to rotate it. So if the sphere has less rotational inertia, that means it's going to be easier to rotate, which means more of its moving kinetic energy gets turned into rolling kinetic energy. All of this seems like it would make it unfair. However, they said the total kinetic energy, which means rotational and translational, both get added together. So that means you don't even have to know any of this. Basically, You can ignore everything I've said, even though I think it's worthwhile to say, and say, okay, how does the total energy of a cylinder and a sphere compare as you roll them down the ramp? And the answer is potential energy turns into kinetic energy. So they should both have the same gain in kinetic energy, because the same joules of potential turns into the same joules of kinetic. So the answer should be C. Wait, D? D. I think D. Gravitational force does the same work. Same Fg, same D, same work. Hope that helps. All right, so 54, I see a graph. I'm immediately looking at it. It's a force distance graph. That should immediately pop out to you. Oh my God, this is a work graph. Area under the curve equals force times distance, or length times width. I don't know how that happened, which is work, which is equal to the change in energy. Now I'm looking at the answer choices. They're numbers, which means we're doing a calculation, and they're measured in kilograms, which means we're calculating mass. Now, without even looking at this, part of me thinks, oh my God, I could probably start this right now. I could set the area under the curve equal to the kinetic final minus kinetic initial, and then I can use the kinetic energy equation to solve for mass. So FD equals KF minus KI, or 1/2 mvf squared minus 1/2 mvi squared. But then I realized, oh my gosh, I don't know the final velocity, initial velocity, or the distance. You need this, you need this, you need this, and we need this. Oh, we have this, right? FD. But then we look at the problem and we immediately see all of the information we know, or we need. We know the final velocity is 3. The initial velocity is 0, which I already have these in my diagram. Final velocity is 3, initial velocity is 0. And the left side of the equation, work, equals 0.09 times, or 1/2 base times height because it's triangle. So 1/2 times 3 times 0.9, which equals Vuja. So you set Vuja equal to Kf minus Ki. You plug in your V's, and you find that the initial velocity was 0. So Vuja equals 1/2 mvf squared. You plug in mass, you do a little algebra, you solve for VF, and that one should come out to be 0.03 kilograms if you did your math correctly. All right, so I'm going to go ahead before we even look at 55 and say it is a tad unfair, because we haven't really spent a whole lot of time discussing rolling kinetic energy. But I want you to realize, or at least see this question. We will get to this when we get to the rotational unit. But for now, suffice it to say that if an object is rolling, it does have kinetic energy. So if this satellite is spinning because they turn on the thrusters in the problem, then it has rolling rotational kinetic energy. So that's necessary before you go into this question, but it should only take 2 seconds to be like, okay, I recognize that it's rotating faster, rotating slower, rotating at the same speed. And then our answers are in the choice of a table. I love those. That makes it easy for my brain. So basically, this satellite is orbiting the Earth. Why are they the same size? Why is the satellite as big as the Earth? It doesn't matter. And it's orbiting in a perfect circle. And then the thrusters turn on as it's orbiting. I'll draw an arrow of orbit. Thrusters turn on, it's going to start spinning faster, but none of them are an unbalanced force forward, backward, towards the center, or away from the center. It's just going to make it spin faster while it's orbiting. So it won't change the orbit. So no effect, no effect. That eliminates B and D. And then we need to figure out the mechanical energy, or total energy, of the satellite Earth system. Well, first of all, it loses chemical energy, the rocket energy, that turns into rotational energy. But they didn't say of the satellite Earth, satellite Earth thruster system, because that would include the fuel. In which case, energy would be conserved. Fuel energy would turn into rotational energy. But they're not including that, which means now we have an unbalanced force, this thruster force, adding rotational kinetic energy. So that should increase, which means your only answer left is C. All right, so for this question, it's really not that bad. I look at the diagram, I see a spring in position A. I look at the spring in position B, it looks like it got squished. I don't know if it was dropped or pushed down. And then I look at the answer choices. I don't know if you can see my mouse, I'm hoping you can. But we see it's all about the energy. The energy is increasing or decreasing. And then they have a quantity in the right part. I love when answers are parallel like that, where you can see this is how these answers are different. So try to pay attention to those, look for them, because it makes what you're reading for in the problem very simple. And then we go back and read the problem. They give us the mass, the K value of the spring, and they ask us for the change in energy of the block spring earth system. Okay, so the block means we're considering kinetic energy, the spring means we're considering spring energy, and the earth means we're considering gravitational potential energy. So our mechanical energy are all of the things listed in our system: kinetic plus spring plus gravitational. But they ask us for the change in kinetic energy. So think about what happens to each of them. Well, it starts at rest and ends at rest. So the K value remains the same. The spring value, the spring gets compressed more, which means we're adding spring energy. Gravitational, it's lowering down, so we're losing gravitational energy. So your change in energy should be equal to the sum of an increase in spring but a decrease in gravitational. I think this is why most people would get it wrong, is they would just consider how much spring energy has been added and not consider the fact that gravitational energy has decreased. And once you see this, the problem becomes very simple. You insert your equations for each type of energy, you insert your values, you do a little bit of algebra, and you get an answer of negative 1.5 joules. So the answer for that one should be A. Whoops. All right, so looking at 57, and here's another trick you should get good at, is the question is short, the answers are long, the answers have no pattern. I'm not going to read the answer choices on this one. I'm going straight to the question. And you find that it's the Mars orbiting around the sun, also the same size. And they're talking about when it's getting close to the sun. So as Mars goes from position A to position B, what can justify the gain in speed? Oh my gosh. This is exactly the case as when you fall from a building. You start with potential energy, turns into kinetic energy. So before I even see the answer choices, this is the thought that's in the back of my head as I'm looking for potential turns to kinetic. So A, as Mars gets closer to the sun, the Mars-Sun system loses potential energy and Mars gains kinetic energy. Right off the bat, I'm thinking A. B, a component of the gravitational force exerted on Mars is perpendicular to the direction of motion. That's true, because it's moving tangentially and the force is always towards the center, causing an acceleration and a gain in speed. No. Okay, so forces only cause increases or decreases in speed, because that's what this is all about. What causes the gain in speed? Forces cause an increase or a decrease in speed when they're in the same direction as the motion, right? If you push a car that's moving forward, it's going to get faster. If you push a car that's moving forward backwards, it's going to get slower. But a perpendicular force won't change its speed, it's going to change its direction, which is what happens with this. So I'm ruling out B. C is the torque exerted on Mars. Oh gosh, we haven't done torque yet, but it's also not necessary. During the segment, increases as the Mars-Sun system's angular momentum. And again, we'll get into angular momentum later. If you're looking to get a head start, it's this equation. I'm not touching it. I don't know what it is. I'm just going to skip it and hope that A, which I feel very confident already, is right. And D, the centripetal force exerted on Mars is greater than the gravitational force during the segment of orbit, causing Mars to gain speed as it gets closer. Centripetal force, well, that's Fg. which is equal to g m1 m2 over r squared, gets greater. I would agree with that statement because the radius gets smaller, which means this whole side should get bigger. But that's not what causes it to gain speed as it gets closer. Because again, that force is perpendicular to the direction of motion. So we can rule that out for the same reason we ruled out B. So our answer of A is in fact correct. All right, so 58, there's a lot to unpack here. I immediately see a velocity time graph, and my first thoughts are slope equals acceleration, and area under the curve equals velocity times time, which is displacement. Meters per second times second is meters, right? And then I look at the answer choices. We're looking at between T1 and T2, T2 and T3, and so during phase 1, during phase 2, during phase 3. So we're trying, and then I go back and read the question. There's a varying net force that causes net work on the box. This is the total work. This is not the work from one of the several forces, which makes this problem not awful. And then work equals force times distance. Could you do this more simply with work equals the change in kinetic energy? I think you could. You absolutely could. If you want to, just hang on while I'm talking about what I'm going to talk about, and then I'm going to talk about that. Actually, you know what? I'm going to skip my thought process from before. Work equals change in kinetic energy. My goodness! And kinetic energy is 1/2 mv squared. I'm sorry that I changed thought processes, but I really haven't said anything that I don't want to say. Kinetic energy is 1/2 mv squared, so the change in kinetic is proportional to the change in velocity, right? So if we're increasing velocity, we're going to have positive work. Work is adding energy to the system. My goodness, that rules out B and C. During phase 2, it's a constant velocity, which means the net work is 0. That rules out B and D. So right now we've already chosen A, but let's confirm it. During phase 3, it's slowing down, which means work is removing energy from the system. So it's negative work. That's so much more elegant than I thought it was. My goodness. Cool. All right, so I look at this, the problem's about as long as the answer choices. I'm going to read the problem first because the answer choices, I see the word graphing in each of them, which means I'm going to pay attention to graphing. What am I graphing? Vosja versus Vosja, and use slope or area under the curve. So actually I did look at the answer choices first, sorry. And then when you read the question, they give us these supplies, spring scale, a meter stick, and a stopwatch, and whenever you are given supplies, you should think about, okay, what does each give me? Well, the spring scale gives me force, the stopwatch gives me time, and the meter stick gives me displacement. This rope is being pulled by a constant tension force. I should have said that at the beginning. So which graphical analysis technique, that's fancy for make a graph and use slope or area under the curve, because those are the only two things we care about with any graph, except for if you're picking out data points, which rarely happens, will allow the student to determine the work done by the string. Well, the work done by the spring is equal to FD. And that's a length time, that's a product, which means our graph is going to have to be a product. So you're going to have to graph force and displacement. So we're going to graph the force as a function of displacement, and we're going to multiply them to get area under the curve. So force is a function of distance, calculate area under the curve. That tells me it should be D. It's not slope because that would be F over D. It's not force is a function of time for B, force versus time. Area under the curve would be F times T, which is impulse. We haven't even touched that yet, we will. And force versus time, and calculate the slope, force divided by time. What would that be? That's nothing. That's a Newton per second. I don't know what that would be. I don't think it's anything. But the answer is D for 59. All right, so for 60, we have three objects that are initially very far away. Again, the first thing I'm looking at is diagram. I see three objects of different mass at radius r. And then I'm looking at the answer choices. My answer choices tell me how I'm going to approach the problem. They're all in terms of G, M, and R, and it looks a lot like the potential energy equation. So I already know what I'm going to be doing before I even read the question. But then they say some information. They're initially far away. Whenever you see the words "far away" in a College Board physics problem, what they're saying is they're far, meaning so far that in the next line they say where the total potential energy of the system is zero, meaning they have no gravitational attraction towards each other. Do you have any idea how far you would have to be for that to be the case? An infinite amount, because if there's even any two objects universe apart, they're still going to be attracted to each other. So they're saying so far away that you can ignore it. It's essentially zero. It's negligible. That's what they're saying in that first sentence. But then they bring them into whatever diagram we have in this problem, and you're supposed to calculate the total energy. Well, in the top left, I have that equation to calculate the potential energy between any two objects. So you're going to calculate it between object A and B, between B and C, and between C and A. Calculate the potential energy of one pair, calculate the potential energy between the other pair, and calculate the energy between the third pair, which I've labeled 1, 2, and 3 on my diagram. So you're going to find each of them separately using the equation, which I've done here, and then you're just going to add them. That's the total potential energy of the system, and you're going to get 5 gm squared over r. I would pause here if you need to follow my work a little more closely. All right, so 61, I'm quickly glancing at the diagram. We have two blocks both being pulled with force F. I'm looking at the diagram. We have force versus time. Slope and area under the curve don't really seem to give me a whole lot for that. And then I'm looking at the answer choices. Block of mass M, block of mass 2m, both have the same power. So I'm comparing power of the two blocks, which one gets more power. And then when you read the question, you find out that's exactly what's going on. To do this, you need to look up the power equation, which is equal to work divided by time, and work is equal to FD over T. So whichever one has the biggest FD over T gets more power. And we know during the first second, there's no force. So during phase 1, the force is 0. During phase 3, the force is 0. So we only care about this little segment in here during phase 2, or between seconds 1 and 2. Well, they already told us they're both being pulled with the same force F, so that's constant between block 1 and block 2. They're both being pulled for 1 second, so that's constant between block 1 and block 2. So now we need to figure out which one has more distance. And you could reasonably say, oh, same force, same time, same distance, but no. Think about pulling a small object versus a big object with the same force. Which one's going to travel a further distance in 1 second? Think about carrying a heavy box versus a light box. The light box is going to go way further with the same force. So block 1 has way more distance, technically twice as much, right? I think. Yeah, double the mass, half the acceleration. So I don't know if you could say twice the distance, but more distance, which means more power was added to it. So the answer for that one should be block A. If you guys stuck with me through all of this, you're a freaking champ. I don't know. Come in tomorrow and tell me the narwhal bacon's at midnight, so I know you watched it. Peace out, and I'll see you in the next one. Have a good night.